Okay, I started to explain something over here and realized that when I wrote down the wronskian, I was careless. The wronskian is clearly 4e to the 6t here. We'll come back to that. I want to make sure I've mentioned this. I might have done it in the video that I was also explaining this, and I might have done it elsewhere. But after we get our z1 and z2 by solving these two equations, well, then we have our z vector. How do we solve the original equation, which was in terms of y? We changed our variable to z so we could get equations in two equations, each in a single variable. We've got to transform that back to our y. Okay, well, that's easy to do. Our change of variable is y equals tz, and we just calculated z1 and z2, which make up our z vector, so we just multiply by our T matrix, our column of eigenvectors matrix that gives us, and that we use to get the similarity transformation. And that's the matrix we use here to get our y. So we just multiply the z that we get from solving these two equations by that transformation matrix. We get our solution for y. Okay, now over here, you are asked to write out the psi of t, psi inverse of s matrix for a given system. The system in number 3 was a system that uses the same matrix that we started with, and it's not up here anymore, but it uses that matrix, and it's just the homogeneous system for that matrix, and we get the same eigenvectors and the same eigenvalues. It's just that when we're solving the system, we're going to do e to the lambda t times the eigenvector, okay, to get the solution vector. So it's e for lambda equals 1, the eigenvector was 1, negative 2. We do e to the 1t, or just e to the t times this, and we get this that I don't have to read to you. Okay, for lambda equals 5, we're going to do e to the 5t times the corresponding eigenvector. That eigenvector was the 1, 2 vector. And we get, again, I'm not going to read it to you, there it is. So our psi matrix is just the matrix that consists of our two fundamental solutions, our fundamental set of solutions. This does form a fundamental set. We put those column vectors into the columns of our psi matrix, and there we have it. Now, the wronskian of that matrix, and this is where I messed up, I had 6 written here, I got that 6 in my head or something. But e to the t times 2e to the 5t is what? 2e to the 6t. And over here we have a negative 2e to the 5t times e to the t, which is going to, and we're going to subtract that, so we're going to end up with another 2e to the 6t, and our wronskian is going to be 4e to the 6t. The inverse of that matrix, we just flip our main diagonal and change the sign on our second diagonal and divide by the wronskian, and I took that 6 out and didn't replace it with the 4, but there it is, and then we get what? We get 2e to the 5t divided by 4e to the 6t. Well, that's 2 over 4 is 1/2, and e to the 5t divided by e to the 6t is e to the negative t, so we get e to the negative t over 2. Over here, well, we get what I say, okay? We get e to the negative e to the negative t over 4 when we divide this by this. Dividing this by this, we get e to the negative 5t over 2, and dividing this by this, we get e to the negative 5t over 4. So that's our psi inverse matrix. Now, we calculate psi of t, psi inverse of s. I'm not telling you why. This is a propagator matrix. We'll see how that works in the next class. I just want to get this calculation out of the way so you know what this step is. So, we have our 5ts, that's our propagator matrix. Psi of t times psi inverse of s. Well, here's psi of t, so we just write that down. And here's psi inverse. Now this is psi inverse of t. We want psi inverse of s, so we just write this matrix down, but we use s for our variable instead of t. And yeah, okay, I'm sorry, I was looking at this. So we use this matrix, because of course this one has to be divided by this. We use the matrix that we get when we complete constructing the inverse matrix. And just replacing all the t's here with s's, this is what we get. Now that's an s, it's not a 5, it's a little hard to distinguish. And that's an s, and they're both negative s's, and that's a negative 5s, and that's a negative 5s. Our denominators are 2, 2, 4, 4. So what we want to do is we want to multiply those matrices. Now I'm not sure I'm going to be able to write this out all that well with the space that I have here, but let's at least start. So this row times this column, we have an e to the t times e to the negative s over 2. That's going to give us e to the t minus s over 2. And let's see, multiplying this row by this column, we get e to the t minus s again, but it's going to be negative. Uh-oh, wait a minute. I didn't complete this one. Okay, it's late in the day, I'm sorry. So we get e to the t minus s over 2 from this one. Multiplying this one by this one, we get e to the 5t minus 5s over 2. So that would be plus e to the 5 times t minus s. And I'm sorry, I just can't get this chalk to come out legibly in this particular board. And that's over 2. Okay, so that's a t minus s. You can't read that t, I'm sorry. And I think you can barely read this one. Okay, e to the quantity t minus s. Okay, so we have a t minus s here, we have a t minus s here. Now we're not going to do any more about factoring that or combining the two exponentials, and in fact we really can't. We can factor an e to the t minus s out of it. That wouldn't be worth doing anything with. The point is we get a t minus s here and we get a multiple of t minus s here. And when we do this row by this column, the same thing is going to happen. We're going to have an e to the t with an e to the minus s. So we're going to have a t minus s for our exponent. And when we multiply the e to the 5t times e to the negative 5s over 4, we're going to have an e to the 5 times t minus s. And I don't have room to write all that out. I'm going to come down here and I'm just going to put dots here. There's something that goes there. You can figure it out. You can multiply it out. And there's something that goes down here, this row times this column. But I'm going to do this row times this column just to illustrate again. Okay, I have negative 2e to the t times negative e to the negative s, that divided by 4, which is going to give me 2e to the t minus s divided by 4, which is e to the t minus s over 2. Now that one came out more legible than we might have anticipated. You can probably read that. Now let's see if our log holds. Okay, 2e to the 5t times negative e to the, I'm sorry. Yeah, 2e to the negative 5t times e to the negative 5s over 4 is going to give us then e to the 5 times t minus s. And I'm sorry, it's not coming out as legible as I'd like, over 2. Okay? So this is our diagonal, and yeah, I just did that because I had room to do it. I didn't have room to do this one or this one in any semblance of legible fashion. So this is one entry. This is another. Okay, well, I just want you to be able to multiply these, and then I want you to understand that this matrix here is a function of t minus s. Okay, so that's really kind of important, and that's one of the things I really wanted to illustrate here. this is a function of t minus s. Since the only variables that occur can always be put in the form t minus s, and that's going to be very important when we try to apply the propagator matrix. Now I think I said this, but I'm going to say it again. You really want to know about, yeah, I know I said it, but you really want to know the Taylor series of e to the x, also sine x and cosine x. They're going to be important, and not just now. They're going to be important for the last couple of weeks. And the Maclaurin series of e to the x as well as sine x and cosine x. Then we observe that if a is diagonal, it's really easy to do the nth power of a. If you have a diagonal matrix like this and multiply it by itself, you get the square of the diagonal matrix. And what you're going to get is just the square of this and the square of this in your diagonal. You can verify that for yourself. And if you want to then multiply by this again, you're going to get the cube of this number and the cube of this number on your main diagonal. You're still going to have zeros over here. You can write that out. Go ahead and write out the first 5 or 6 powers of this. Not difficult to do. So that you can convince yourself that we can easily find the nth power of a diagonal matrix. Well, if you can do the nth power diagonal matrix and you understand the Taylor series of e to the x, you see that the Taylor series of e to the x is just a sum of multiples of the powers of x. You know, x to the 0, x to the first, x to the second, and so forth. So we could do e to the a. We could do e to a matrix. Okay? We could expand it in a Taylor or Maclaurin series. So we could write out the exponential of a matrix or a sine or a cosine. That's kind of a neat idea. So it's really kind of worth thinking about.